Okay, we're starting a new chapter. This is chapter 4, exponential functions. We've actually seen them in some of our previous examples, we just never called them that. So section 4.1, exponential growth and decay. Okay, look at exponential growth and decay. Again, we've seen this before without actually saying it. Definition. We've got a two-part definition, one for growth, one for decay. Number 1 says, exponential growth means that a whole number increase in the independent variable results in an increase in the value of the dependent variable that is a multiple of the previous value of the dependent variable. Okay? So a whole number increase in the independent variable, and the dependent variable will increase by a multiple of the previous value. It's kind of like multiply the previous value by 2 or multiply the previous value by 1.2. Number 2, exponential decay means that a whole number increase in the independent variable results in a decrease in the value of the dependent variable that is a multiple of the previous value of the dependent variable. So it's kind of like multiply the previous one by 0.7 or multiply it by 0.3 or something like that. So we're going to take a look at what this looks like graphically. So we're going to illustrate exponential growth and exponential decay on the next slide. Okay, so that way when you're trying to decide will an exponential model work, you'll want to know, do your data points kind of line up the way these graphs are going to look. So this is exponential growth. So the y values double with each integer increase in x. Like here I'm at x equals 0, the y value is 2. When I go to 1, it's now at 2, 1 times 2. If I go to 2, I'm now up at 4. 2 times 2 is 4. If I go to 3, it's up here at 8. So I'm almost off my graph. And 2 times 4 is 8. So every time I increase by 1, I multiply the y values by 2. So that's exponential growth. I could also multiply by 3 or multiply by 1.4. I just picked something easy that I could see. This one is exponential decay. The y values are halved with each integer increase in x. So again, here I started with x being 0 and y is 1. When I went to here, x is 2 and now y is a half. I go to here and now y is a fourth. So I'm multiplying each y value by 1/2. One other way of looking at it is I'm dividing by 2. Again, I just arbitrarily chose the 1/2 because it would be easier to see. So this is exponential decay. The graph is decreasing as we go from left to right. Going back to the previous one, it was increasing as I went from left to right. Notice this is concave up. This is also concave up. Definition. The form of an exponential function with initial value p and base a is given by f of t is equal to p times a raised to the t power. If a is greater than 0, then the function demonstrates exponential growth. If 0 is less than a is less than 1, in other words, a is a fraction between 0 and 1, then the function demonstrates exponential decay. We don't allow a to be negative. We don't allow a to be 0 either. So if the base of the exponential function is a number bigger than 1, it's growth. If it's a fraction between 0 and 1, it's decay. In the illustration that we had above, for growth, p was equal to 1 and a was equal to 2, and the one for decay, p was equal to 1 and a was equal to 1/2. So the base is what we multiply the function values by when the value of t increases by 1. So in the case a is 2, we double every time. If a is 3, we triple every time, and so on like that. Things that grow and decay exponentially are populations. Now, population can be more than just people or animals. It can be money, it can be weight, it can be mass, it can be a lot of things other than just actual living organisms. since exponential functions deal with populations, the base A is also called the growth factor or the decay factor. Okay, so you're using growth factor for increasing, decay factor for decreasing. So the decay factor is the base of the exponential. Remember, the P is the value you started with. Some examples. Number 1 says, a radioactive substance has a decay factor of 0.438. If a sample started with 200 grams, and time t is measured in years, find the following. In part A, a function q of t that gives the quantity present after t years. How many grams are present after 7 years? Round your final answer to the nearest hundredth of a gram. Part C, graph q of t from t equals 0 to t equals 20. Use a suitable window. And in part D, in how many years will there be 100 grams of the substance? Round your final answer to the nearest hundredth of a year. Now this is called the half-life, because notice 100 is half of what I started with. So question D is actually asking you to find the half-life. Our solutions. Okay, in part A, Q of t is supposed to equal the initial amount, the initial amount times the decay factor raised to the t power. So are we given these values? Okay, we started with 200 grams, so there's our initial amount. The decay factor of 0.438, so we know the decay factor. So Q of t is going to be 200 times 0.438 raised to the t power. There's your A. Okay, now since I know I'm going to have to graph this and everything, let's go ahead and get out our calculator. So, calculator. Okay, let's go ahead and set up our window. Notice we're starting with 200, so my y max should be something bigger than 200. I'm going out to 20, so I'm going to let my x max go out to maybe 25. So let's see, for our window. Okay, negative values don't make sense, so 0 for the minimum. And again, for the maximum, let me go out to 25. And, no, the system says 20. I better read what it says. Let me go to 20. And my x scale, I don't know, multiples of 2. The y min, okay, 0 doesn't make sense. Or excuse me, negatives don't make sense, so 0 is the smallest amount you can have. And since the maximum is, since we started with 200 and it's decaying, so let me maybe have, I don't know, 210. And let's have our y scale to be 10. Okay, so let's quit that. And let's go ahead and put the function in the y1. So it's 200, open the parenthesis, 0.438, close parenthesis, raised to the t power. Okay, and we can get out of that. Now, for part B, we're going to know how many grams are present after 7 years. So that means we're going to let t be 7 in this. So we're going to round your final answer to the nearest hundredth of a gram. So we need to find q of 7. So we've already put it in our calculator, so let's take out the calculator. Bars, 5 R's, function, enter, and y1 of 7. Okay, to the nearest hundredth of a gram, we get 0.62. Okay, not a whole lot. So I put the q of t into y1, again that, so to the nearest hundredth, 0.62 grams. Yeah. So it's decaying kind of rapidly. Okay, part C for the graph. Okay, again, I made it slightly bigger for here. So that's what does our graph look like? Using the windows I had set up here. So let's see, when we clear that out. Let's just go ahead and say graph. Okay, notice it's almost down to 0, so you can hardly tell any amount is left. Can you still see the slight blue line there? Notice it decays incredibly fast to begin with, and then it finally starts to level down. Remember, that's what concave up, a decreasing function, means. It decreases, okay, since it's concave up, it decreases at a decreasing rate. So again, kind of a similar window. And again, it's almost 0 there. But you know, we saw that after 7 years, you were down to less than a gram. Okay, for question D, okay, I entered 100 into y2 and found out where they intersected. So remember, this is the crossing graphs method. So if I do that here, I don't really need to change the window though. So let's see, y equals, let's have y2 be 100. Then second calc, intersect, choice 5. y1 is correct, y2 is correct. I'll take 10 as a guess. So it looks like it's going to be in less than a year, right? So we're getting 0.839, etc. So rounding to the correct number of places in about 0.84 years. So less than a year. But again, it was decaying incredibly fast. Question number 2. During the spread of a certain disease, the number of infected people increases by 50% each month. Suppose that initially 10 people are infected. Find the following. Part A, a function n of t that gives the number of infected people after t months. Question B, how many people will be infected in a year? Round your final answer to the nearest whole number, because again, these are people. Part C, graph n of t for 1 year. Question D, how long will it take for 100 people to be infected? Round your final answer to the nearest tenth of a month. Remember, the time is given in months, and we're doing these two questions here in years, so remember, 12 months is a year. So we're given the initial amount, right? 10. Now we're told that the number of infected people increases by 50% each month. That's not exactly the decay factor. It's kind of like we get an additional 50, so that means we have to add something. So our solutions. For part A, n of t again is the initial amount times the growth factor raised to the t power. Okay? Now of course t is understood to be in months. Okay, the initial amount we're told is 10. Okay, so the growth factor is an additional 50%. Okay, we get an additional 50%. So that means we're going to have 100%, what we had previously, plus the additional 50%. So that's 150%. Okay, we've seen something like this before. So as a decimal number, it's 1.5. That's our growth factor. Now, if we were doing something like it decreases by 50%, we would have had 100% minus 50%. Okay, so if you're getting an additional amount, it's 100% plus the percentage given to you. If you're decreasing, it's 100% minus the percentage given to you. And again, the initial amount is 10. So our growth factor is n of t, actually our growth function is n of t equals 10 times 1.5 raised to the t power. And again, since we're going to be graphing all this stuff, let's go ahead and clear out our calculator from the previous stuff. So quit this. Y equal, let's clear that. I can probably leave my y2 at 100 because that's what the question here is asking about, how many people, 100 people to be, how much time for 100 people to be infected. But let's go ahead and change our y1. It's 10, open parenthesis, 1.5, close parenthesis, raised to t power, and it's going to get out the exponent. And let's quit this. And while we're playing with the calculator, let's go ahead and set up the window where it should be. Okay, we're supposed to do this for 1 year, so x-min will be 0. The max will be 12. Whoops, wrong place. Clear that. 0. The max will be 12. Now let's have our scale be 1. What the heck? The y minimum, let's keep it at 0. And I don't know how many people have been infected, so let me leave that blank. Let me leave that at 210 for the moment. Okay, so we're not going to graph it yet anyway. So let's see. Question B, how many people have been infected in a year? So we want to know n of 12, right? So for question B, n of 12. So we're going to evaluate y1 of 12. So vars, y vars, function, enter, y1 of 12. Ooh, I'm getting 1,297 point, etc. So the nearest whole number, 1,297. This is telling me that I probably need to change my Y max to something bigger than 210, right? So, looks like at the end of the year, to the nearest whole person, 1,297 people will be infected. Okay, for question C, we're supposed to graph NFT for 1 year. So notice at the end of 1 year, I see 1,297 people infected. I'm going to have my Y max something slightly bigger than 1,297. Okay, that's the only thing I really need to fix. So to do the graph, I chose 1,300 for the max and multiples of 100 since I'm so far, since I have such a huge range there on the Y's. So if I set up my calculator window, see, I've got to fix my max, right? Y minimum 0, Y max 1,300, and the scale will be 100. Remember, it's going to draw Y2 because I didn't clear it out. So our graph, okay, notice it's growing very slowly at first, and then it starts to grow incredibly fast. Remember, it's increasing, it's concave up, so the rate of increase is increasing. So ignore the red graph for this part of the question. So there's our graph. Again, starts off very slowly, very few people are infected, and then before you know it, you have an epidemic on your hands. Okay, question D, we're going to let y2 equal 0 and find out where they intersect. So remember, I already got my y2 there. So do second calc, choice 5. Okay, y1 is fine, y2 is fine. Go ahead and guess 6, sure, what the heck. Okay, it turns out it's about 5.678, so on. So, same picture we had before. So, in about 5.7 months, 100 people will be infected. So again, medical people want to know this to find out how long do we have before we have a major epidemic on our hands. Now this question, before we get into the next topic here, kind of illustrates something interesting. We're measuring in months, but sometimes you want to know how many hours before something happens or how many years before something happens. So that's kind of our segue into this topic, unit conversions. Now, in our last example, we found the monthly growth factor is 1.5. What if we wanted to know the yearly growth factor? Okay, so if we knew the yearly growth factor, we could then have time t measured in years instead of months. Recall that there are 12 months in a year. That means in 1 year, the monthly growth factor gets multiplied 12 times. So 1.5 times 1.5 times 1.5, which in the language of algebra is 1.5 to the 12th power. Okay, so the yearly growth factor, if you do 1.5 to the 12th power, you get 129.746 if you round to 3 places. Looks rather huge in that respect. So if we were given the yearly growth factor and wanted the monthly growth factor, we would need to take the 12th root, because again, 12 months in a year. Algebraically, it means that we take the yearly growth factor to the 1/12th power. Okay, so to do an nth root, it's the 1 over n power. So a square root is a 1/2 power, a cube root is a 1/3 power. So notice it's kind of a simple thing. It's either the number or the number turned upside down. So we have something in general for this. So in general, we have the following. If there are k smaller time periods in a larger time period, like 12 months in a year, 7 days in a week. Number one, if you're given the growth factor for the smaller time period, then the growth factor for the larger time period is smaller time period growth factor raised to the k power. Now what if you're going the other way? If you're given the growth factor for the larger time period, then the growth factor for the smaller time period is larger time period growth factor raised to the 1 over k power. Let's take a look at some examples of this. So, examples. Number 1 says, the U.S. Census is taken every decade, every 10 years. According to the last 8 censuses, a certain city had a growth rate of 0.358. What is the yearly growth rate for the city? Round your final answer to 3 places right at the decimal point. So again, every time we looked at the censuses, we saw a growth rate of going from one census to the other of 0.358. Now remember, a decade is 10 years. So our solution, so we're given the growth rate for a decade. And again, there are 10 years in a decade, so we're going from a larger growth rate to a smaller growth rate. So you need the fractional exponent. So the yearly growth rate is going to be the decade growth rate raised to the 1/10th power. Okay, now, because some of you may still have the TI-83, let me show you what you need to do on the TI-83. Okay, because the TI-83 still uses the caret, so you're going to have 10 raised to, now because we have a fraction or an operation as the exponent, it must be enclosed in parentheses. So open 1 divided by 10. Now, of course, on the 84s, you will actually see that you are in the exponent, so you won't have to worry about the parentheses. But with the TI-83, you need to. Otherwise, what you're really doing is 10 to the first power divided by 10, which would actually be 1. So when we do this, we get 1.258, etc. So, whoops, I put in the wrong number, didn't I? Let's do the right problem now. So, 0.358 raised to, open parenthesis, 1 divided by 10, close. So 0.9023, etc. to 3 places. Yes, 3 places. 0.902. So now remember, on the 84, you wouldn't need to do that. Let me turn it back on. So clear this out. So quit. So I've got 0.358 raised to 1 divided by 10. You don't need the parentheses because you can see you're in the exponent. And notice you get the same thing, which of course you should have. So 0.358 to 1 power, so you get 0.902 to 3 places. So that's your yearly growth rate. Notice the yearly growth rate is actually larger than the decade growth rate. Number 2. Susie has invested her money in stocks that have a daily growth factor of 1.002. What is the yearly growth rate of Susie's investment? Round your final answer to 4 places to the right of the decimal point. Now, a lot of times if you look at your bank statement, it'll actually tell you the daily percentage, and it'll tell you how many days it was actually being worked on. So our solution. Okay, we're going from a smaller growth rate to a larger growth rate. Okay, so we need the whole number power. So there are 365 days in a year. Unless you're told otherwise, always use 365 days in a year. So the yearly growth rate is the daily growth rate raised to the 365 power. So our daily growth rate is 1.002. We're going to have 1.002 raised to the 365 power. Okay. When you round it to 4 places, you should get 2.0736. Radioactive decay and half-life. Definition. The half-life of a substance is the amount of time needed for half of the substance to decay. Okay, the substance decays into something else, and it depends upon the actual substance what it decays into. Sometimes it decays into something completely new, and other times it just decays into a different isotope of what it is. So if you're told the half-life is 50 years, and you start with 100 grams, in 50 years you're down to 50. In another 50 years down to 25. In another 50 you're down to 12.5, and so on. So in most situations involving radioactivity, the half-life of the substance is used instead of its decay factor. So we need some sort of relationship between half-life and decay factor. So for instance, if a substance has a half-life of 50 years and you start with 200 grams, in 50 years you'll have 100 grams, half of 200. In another 50 years you'll have 50 grams, half of 100. In another 50 years you'll have 25 grams, half of 50, and so on. So notice you just keep having smaller amounts, but it never really completely disappears. So the question then becomes, how long before it's no longer harmful? So you're always cutting it in half, hence the name half-life. Our next examples are going to make the connection between half-life and decay factor. So it might be something that you want to write down as a fact so we can use it later on a test or homework or what have you. So some examples. Number 1 says, a substance has a half-life of 350 years. Find its yearly decay factor. If nothing else, I have years and years. So our solution. Oh, round your final answer to 5 places. Okay, lift that off. So our solution. Okay, 1 half-life, the substance decays by a factor of 1/2. Okay, remember, 1 half-life is 350 years. So in T half-lives, the substance decays by a factor of 1/2 to the T. You know, half times a half times a half, and so on. Since the half-life is 350 years, in 1 year, there are 1 over 350 half-lives. Notice you just take 1 divided by the number of 1 divided by the half-life. So the yearly decay factor is 1/2 raised to the 1 over 350. Remember, T was the number of half-lives. When you crunch all that out, you get 0.99802 rounded to 5 places. So you now know to go from half-life given in years to go to the yearly decay factor, take the half-life raised to the 1 over the half-life. As long as this time matches this time, that's what you do. So if you're given that the half-life is 12 days, the daily decay factor would be 1/2 raised to the 1/12th power. Number 2. So note in general, decay factor is equal to 1/2 to the 1 over half-life power. Again, that's provided these times match. If they didn't, you would then have to do what we did in the previous section on the unit conversions. To get half-life from decay factor, we need another function. So number 2, a substance has a half-life of 700 years. If you start with 600 grams, find a function Q of T that will give the quantity of the substance that remains at the end of T years. Round all values to 5 places to the right of the decimal point. So let's see, we're told the initial amount, we just don't have the decay factor. So our solution. Okay, the decay factor is 1/2 raised to the 1 over 700. Because again, years, and we're looking for years. So that's your decay factor, which when you take out to 5 places, 0.99901. So there's our decay factor. There's our initial amount. We have everything we need. So Q of t is 600 times 0.9901 raised to the t power. That's the end of section 4.1.